discuss an example about finding the Jordan canonical form of a matrix. And this example comes from the very beginning of chapter 12, even before section 12.1 actually begins. And the question is, what is the Jordan canonical form of the following 3x3 matrix? So we have this matrix A, and we want its Jordan canonical form. So we know that it's enough to find the elementary divisors of this matrix. And then we can write down the Jordan block corresponding to each elementary divisor. And that'll give us a block diagonal matrix in Jordan canonical form that this matrix A is similar to. And if we know the invariant factors, that's enough to determine the elementary divisors. So all we need are the invariant factors of this matrix. And we saw that for 3x3 matrices, there's this little trick that in order to determine the invariant factors, all we need is the characteristic polynomial and the minimal polynomial. The characteristic polynomial is just some determinant that we can compute. And the minimal polynomial, once you know the characteristic polynomial, there are only a couple of possibilities, and you can check and see which one of them actually is the minimal polynomial, and that will give you the invariant factors. So by doing that, computing the characteristic and minimal polynomial, we can get the invariant factors, we can get the elementary divisors, we can write down the Jordan canonical form of this matrix. So that is some matrix that it's similar to, such that it's in Jordan canonical form. That means, so if your Jordan canonical form is some matrix, let's say C, then there exists an invertible matrix P so that C equals P inverse AP. If you go through this find the characteristic polynomial and find the minimal polynomial procedure to determine the invariant factors and find the Jordan canonical form, it's not at all clear to me how you find this matrix P. So this is really similar to something we talked about for rational canonical form. So I'm going to go through this process of finding the Jordan canonical form by diagonalizing this matrix x times I minus a, finding the Smith normal form of this matrix, because the procedure that we do to diagonalize is going to be exactly the thing that we need. It's going to give us all the information that we want in order to find that invertible matrix P for which C equals P inverse AP. Also, this is good practice, so it's a little tricky to diagonalize these matrices, so I wanted to do another example for you in lecture. All right, so what is x times I minus a? It's x minus 9, x plus 2, and then the rest of the entries are just negative. And my short-term goal is I want to get a 1 in the top left corner here. And I see a little nice trick that if I add the second row to the first row, I'm going to get x plus something, and I can cancel the x's and get a unit in a nice way. So if I add the second row to the first row, here's what I get. X minus 5, x minus 4, negative 5 plus 3 is negative 2. Then what I'm going to do is I'm going to subtract the second column from the first column. So like x minus 5 minus x minus 4 is negative 1. So I want a 1, so I'm going to subtract the second column from the first and then multiply the first column by the unit minus 1. And that'll give me 1 x minus 4 minus 2, right? Like 6 minus 4 is 2, and then you multiply by minus 1. And the rest of the entries are unchanged. Now I'm in good shape. I have this 1 up here. So what I'm going to do is multiply x minus 4 times the first column from the second column, and I'm going to subtract, or let me say it this way. I'm going to add twice the first column to the third column to zero out these entries in the first row. And OK, so what do I get? I'm taking x minus 4 times the first column and subtracting it from the second column. So I get 0. And then whatever was in this entry here, x minus 4 squared. And then minus 2 times x minus 4 is minus 2x plus 8. So this 4 turns into a 2x minus 4. OK, so now I'm in good shape because I have this 1, 0, 0 in the first row. So I can just zero out everything below the 1 without changing anything. Here I've just expanded this complicated entry in the middle. So Now I have to decide what to do with this 2 by 2 block. So I'm never changing this one. The first row and column are now set. I'm not going to change them. I want to find another 1 somewhere if I can. And I can see in a nice way that if I take twice the third row and add it to the second row, I get a -1. Not quite a 1, but almost a 1. So I'm going to do that. And now this minus x squared plus 9x minus 16 becomes minus x squared plus, we're adding 4x minus 8. So we get 5x minus 8. We have this -1 here. And OK, I could now scale the last column to get a 1. But the same idea, what I'm going to do is just take x squared minus 5x plus 8 times the third column. And so that these will be equal, and I'll subtract that multiple of the third column from the second column. So I'm going to multiply the third column by, I'm going to add whatever multiple I need of the third column to zero out this entry here. And what you see is x minus 2 divides both of these things. So you can factor out an x minus 2, and you get third column unchanged, 0. And then what you get is x minus 2 times 2, which is from factoring out the x minus 2 here, and then minus x squared. Oh, I'm missing like a sign in here. This should be a plus. Minus x squared plus 5x minus 8, right? The negative of this entry, and then x minus 2 here. And now I can multiply the second row by -1 to make this a 1, and I can zero out the entry in this corner here. And now I can just factor this thing. And what you see is this becomes a -6. This is -1 times x minus 2 times x minus 3. So you can also multiply this second column now by a -1. And now what we have is nice, is 1, 0, 0, 0, 0, 1, 0, x minus 2 squared, x minus 3, 0. And I can swap rows and columns. So I'm just going to swap the second and the third column. And now I have a matrix that's in Smith normal form. And I can just read off the invariant factors from this matrix. So we see that the invariant factors, there's a single one. It's x minus 2 squared times x minus 3. And by factoring this single invariant factor, I get the elementary divisors are x minus 2 squared and x minus 3. So I'm going to pause and erase just to get some more space. And we'll write down the rational canonical form and the Jordan canonical form of this matrix. By diagonalizing the matrix x times I minus a, we saw that its invariant factors are one single invariant factor, x minus 2 squared times x minus 3. And its elementary divisors then come from factoring. You get x minus 2 squared and x minus 3. Expanding out this one invariant factor and writing down the coefficients, we see that the rational canonical form of A is this matrix B, 0, 1, 0, 0, 0, 1, 12, minus 16, 7. It's the companion matrix of this single invariant factor. The Jordan canonical form of this matrix is the 3 by 3 matrix that has one Jordan block corresponding to each elementary divisor, has a 2 by 2 Jordan block corresponding to the elementary divisor x minus 2 squared. So 2's along the diagonal, 1 on the first super diagonal. And then it has a 1 by 1 Jordan block corresponding to the elementary divisor x minus 3 to the first, 3 on the diagonal. So we could have done all of this without diagonalizing the matrix, because all we needed was the characteristic polynomial and the minimal polynomial to find the invariant factors in the elementary divisors. But the fact that the rational canonical form of this matrix is this B here means that there exists an invertible 3 by 3 matrix, let's call it Q, with entries in the rationals such that B equals Q inverse AQ. How do we find this matrix Q? Well, we talked about that in lecture 4. We talked about the invariant factor decomposition algorithm for an F bracket X module. And we said that you can answer this question for matrices in the same way by building a vector space and then a linear transformation from your matrix and applying the same algorithm. Or you can phrase the whole algorithm just in terms of matrices without reference to the vector space or linear transformation or F bracket X modules at all. So we saw how to do this. And this, we really did need to diagonalize this matrix x times I minus a. We don't know how to do this by just computing the characteristic polynomial and minimal polynomial. So what about the analogous question for the Jordan canonical form? We know that there exists a 3 by 3 matrix P with entries also in Q such that C equals P inverse AP. And okay, so now we have to be a little careful because it's really important in making a statement like this that the field that you're working over contains all of the eigenvalues of your matrix. And it just so happens that the eigenvalues of this matrix A are just 2 and 3. So Q does contain them all. So there is such a matrix over Q. We didn't actually know that Q contained all the eigenvalues of this matrix until we computed the invariant factors. But now we know we're okay. Like in general, even if your matrix, even if your matrix has entries in Q, you might not find some matrix with entries in Q that gives you the Jordan canonical form. So you might have to go to some bigger field that contains all of the roots of all of the eigenvalues of your matrix. So we'll talk more about that when we talk about extensions of fields coming up soon. But anyway, in this case, we know that there exists this 3 by 3 invertible matrix P with entries in Q such that C equals P inverse AP. How do you find it? So the answer is very, very analogous to this question about how you find this matrix Q. And it follows a similar procedure to the invariant factor decomposition algorithm for f bracket x modules, except now it's the elementary divisor decomposition algorithm. And we'll talk about that in the next video.